So the specific use case that Geopandas tries to solve is if you have tabular vector data, so if you have points, polygon, line strings, so the things that you use to manipulate shape or import this morning. But as also shown, typically have attribute data. Yeah. So, yeah, okay, thank you. So the specific use case that Geopandas is trying to fill in, if you have tabular vector data, you have a geometry object, you have a certain point, but you have attributes attached to it, or properties are it's called in Fiona. And typically you have a lot of those points, and each of them have those attributes. So that gives you a tabular data structure that you would like to work with. And that's what Geopandas is doing. It's combining those shapely objects and Fiona to import them with Pandas, which provides the tabular data structure. Make this a bit bigger. So I will start with the first notebook, Introduction, Geospatial Data. Like this. So the first thing, if you want to work with geospatial data, you need to get them from somewhere. So you can start with importing them. In the morning we saw how to do it with Fiona, and basically, so Geopandas provides a way to do that. And basically, under the hood, exactly what Martin showed, the code that Martin showed, is happening under the hood in Geopandas. So, for example, here I provided the natural Earth data on some different things. In this case, for different countries, as a shapefile, a little bit processed, simplified version than the one available online, and it's available as a zipped shapefile in the materials. So, how do we import spatial data in Geopandas? There is a read file function, and there you can pass the path to a file, and the different file formats that are supported is basically the most common vector file formats, and in principle it's everything that GDAL and thus Fiona supports. So in this case we can read the shapefile with the countries, and so since what is returned is still a data frame, or at least a subclass of a data frame, I can look at the first rows with head, and you will see here we have geometries and we have some other columns. So the countries are polygons, so the geometry column contains, each row is the data about one polygon, and some of the attributes, so the name, the population of that country, etc. Just like Pandas, Geopandas also provides some quick plotting. It will not be the most beautiful plots, but it gives you a very quick access to visualizing the data. So you can see that here, so the data included in this data set are the countries of the world. What is important to know is that if I look at this countries object, so it's a Geo Data Frame. And what is a Geo Data Frame? In practice, or at least what you need to know about it, it's like a data frame, but it has some added functionality. We will see quite some extra methods that are related to spatial analysis, some extra spatial methods, and it always has at least one column with geometrical data. case, it's the geometry column. It doesn't need to be called geometry, it's tracked under the hood. But if you import it from a certain file format, by default, Geopandas will always use geometry as the name for the geometry column. And this column is also always available as the geometry attribute. Whatever your actual column name for the geometries is, it's always available as the geometry attribute. So in this case, we have our polygons like this. And what is returned here is a geo series, which is a subclass of a series. Again, it's basically a Panda series, but with some added methods to work with spatial data. So basically, yeah. So I already explained this more or less. So we have our geometry column. The other columns are the attributes, or in JSON terminology, properties. And this I also already showed, so that's the geo series. One example of the added attributes is the area, which will give you the area of each of the different geometries. So one of the big advantages of using Geopandas is that the Geo Data Frame is still a data frame, so all functionality you know from using Pandas, you can still you can translate that at Geopandas, and you can still do typical operations on your data frame as you would do in with a normal Pandas data frame. For example, the non-geometry columns, you can calculate the average population of all the countries of the world, or we can do some Boolean filtering based on a certain condition. Let's say I only want the countries in Africa, so there was a column continent, so I do a Boolean, make a condition here to create a Boolean series with which I can filter my original data frame. And now if I plot this geo data frame, I will see it only as the countries of Africa. So those typical operations you are still easily available. If there are any questions about things I do, because I will not explain everything that is more related to using Pandas itself compared to Geopandas, but if there is anything unclear, just raise your hand and ask. I will can certainly explain it. So up to now, the countries data set we have seen has a polygon, geometries, but as Martin explained this morning, you have also other type of objects, and the three basic type of objects are points, lines, and polygons, or you can have a combination of multiple points in a multi-point, etc. So of our countries data set, we will see that this is a polygon object, and I also included two other data sets coming from natural Earth with a different type of geometries. So one data set using with cities. So here you see, if you look at the first geometry of this data set, it's a point, and also a rivers. So a data set with rivers and lake coastlines. And here you see that this is a line string. So a line string is the technical term here for a line. And I won't go into detail here because Martin explained this in the morning. The individual objects, if you access one of the elements in our geometry column, are shapely objects, and we can also construct them ourselves here, for example, like that. So that's also important to know. So all the objects, if you access a single geometry, it's a shapely object. And we will also see that many of the methods that are available on shapely, shapely geometry objects, like you can check whether one point is within a polygon or if two polygons intersect and things like that. All those, the names of all those methods are available on single shapely objects. They will typically also all be available on a Geo Data Frame, but instead of working on single objects, it will then work on, do that operation for all your geometries in the Geo Data Frame. One last thing before I stop talking for a moment and you can do some practice is if you want to plot multiple geodata frames together, you can pass an ax keyword. So for example here, what I did before, I do my countries.plot. I can use, because it's based on matplotlib, I can use some of the typical, you need to know, of course, you need to be familiar with matplotlib, but the terminology of matplotlib to style the polygons. This returns an ax object, and with that, I can add the rivers and cities to the same plot. So, for example, here I plotted part of Africa showing red dots is our cities data set, and the lines are the rivers data sets. Okay, so time for you to do some actual coding. For the exercises, there is some data on the city of Paris included. So two data sets. One is called Paris District UTM.GeoJSON, which is a polygon data set with the different administrative districts of Paris, and one data set with points describing the stations of a public bicycle sharing system in Paris. For the exercises, I will give you some time to do to actually try to solve them and to code a bit yourself. Please first try it to do it yourself. Then, if something is not clear or if you're a bit stuck, raise your hand. I'm here to help you. If you want to check if your solution is correct, or you want to, you're completely stuck and I'm busy, you can always check the solution by uncommenting this cell and then running it, and it will pop up the solution. But please first try yourself.
This file has to be read online. You simply use.
No.
GPU.
So
No.
yeah, that's something I didn't mention. The files are in the data directory. So if you the path just like data slash the file name, that should work. Yeah, and the file name is in the list here.
So if I go in data?
Yeah, so in data.
I don't know.
Yeah, so another note, I forgot to add those data, so I only added them during the tutorial of Martin this, in the morning. So that might be a reason that the data is not there. So you can either re-download or git pull the full repo, or just download the two files from. for some of the, if you just want to read a bit more about how to do the different visualizations, there is a notebook called, I think it's number 4, and the first part has some more details on different options that you have to make visualizations with Geopandas. So the dot plot method, how to customize certain things, is explained a bit in more detail there, in case you, as a reference.
Geopandas works with vector files.
Mm-hmm. Okay, I will go through some of the exercises. Don't worry if you didn't finish them, I will go through them. So to start with, so to read a file, it's read file in Geopandas, and you pass the data set. So it was in the data directory, and then the name for the districts, like this. So read file can read from local files, and it also has basic support to read from a URL, but yeah, that doesn't work always, but Fiona added basic support for reading directly from an URL as well. So yeah, that's for the districts. I will quickly do it from here. The stations as well. So if you look at the district set, you will see that it's basically just an ID and a district name, apart from the polygons of our different districts. And the stations data set has a also a name of the station, but then the number of bike stands there are, and then the number of bikes that are actually at that moment in time they're available, the available bikes. And you can check that both are Geo Data Frames. How do you make a quick visualization of a method of a Geo Data Frame? We use .plot. By default, yeah, so on my screen here, it's actually already quite big because I zoomed in. So maybe the fixed size that I mentioned here. So one of the keyword arguments that is passed through to matplotlib that you can specify is a figure size. Probably this might be, no, it still just fits here. So by default, it uses the style of matplotlib, but you can, in case of polygons, both specify the color of the edges, so the lines around the polygon. For example, I want them in black and the face color in red to make a probably ugly plot. So, but like that, you can specify how it needs to look like. These stations, we can also plot them. So here you see that are points. I can easily give a certain color. For example, I want them all in red. But typically you want your polygons or lines or points, but your geometries colored based on one of your other columns. So in that case, you can pass the columns keyword. What you pass can both be like a discrete, a categorical column, and then it will give one color to each of the occurring values, or it can be a numerical column, and then it will use a continuous color map. So in this case, available bikes is columns. It's column like that. So now you see that at the moment that I download the data, most of the available bikes were around here, which is, yeah, around the Seine, in the river, in the city center. So people were biking in that direction and leaving their bike there. So you had a lot of available bikes over there. If you want the actual color bar, you can quickly get that with legend is true. Sometimes it's a bit harder to then customize it that it looks like you want it to look, but that's how it works. Another thing, if you don't want the axis around it, because in this case, it's in UTM zone, you're not really interested in the labels and the square box around it. You can, for example, use, if I assign this to a variable, that's the matplotlib subplot, and then I can say remove the axis off like this. Of course, here you don't really have a reference on the plot, but we will do that in the next exercise to plot them together. So we plot our stations. We grab the axis, matplotlib axis, and we can, in this way, add our districts to the same plot, like that. Of course, by default, they use the same color, so this is not very interesting. So we can say that we want here a gray color with a certain alpha, I think I asked in the exercise. No, for the districts, like this. Yeah, here I also mentioned how to remove the axis. And let's actually do the same as here. like this. I will make it a little bit bigger, so I can pass a figure size here, like this. So this gives already a bit bigger plot. Of course, here I just start with districts.plot. Of course, you can also create the layout with matplotlib, or create a figure with matplotlib and add in one of your subplots in matplotlib, add there a plot by passing the ax object to the first one as well. I think I did that in the solution here. Yeah. So I directly created a subplot with matplotlib of a certain size and added then the two data sets there. I got a question, can you also add raster data to such a plot? The answer is yes, you can, but not with Geopandas. But since it is just a matplotlib plot, and for example, raster.io, which you can use to import to read raster files, also has some basic plotting functionality, and you can combine them. The only thing is you need to make sure that the projection systems of both data sets are in the same system, so that, for example, you convert your vector file to the same current reference system as your raster data, and then you can easily plot them together. That was some plotting. Here's an exercise to use one of the attributes. So what is the largest district? So I can use my districts geometries. Area is one of the available attributes. If you just look for area, it will give you a new series giving the area of each of the geometries. In this case, I want to know what is the biggest one. In Pandas, you can use IDX max, which is like similar to the argmax of NumPy, but giving you the index at the index label of where the maximum is. And then we can, for example, index our original districts data set with this one. So apparently it's a bit messed up. So apparently the district of, I'm not fully sure how to pronounce it actually. Picpus, so you pronounce the S here. Yeah. Is the biggest district. Yeah, that's true. It's easier. District in Paris. Last thing, last question here was make a histogram showing the distribution of the number of pi extents. It's just also the exercise is basically to remember you. It's still a data frame, so Pandas data frame. So if you access of the stations the column with the number of bike stands, so this has no spatial annotation anymore. This is just a Pandas series, and one of the methods available on the Pandas series is to create a histogram of it, or you could calculate some quantiles or median or mean and things like that. Okay, so up to here, some very basic introduction to Geopandas. The data that you have seen up to now, they were in a certain reference system. So Martin explained in the morning a little bit why and how, why you have a different coordinate reference system and how that works. So I won't go into detail, but mainly highlight a few points why you need to pay attention and on what you need to pay attention when using it with Geopandas. The data frames have a .crs attribute, and this gives you the current reference system of the data if it's known. If you have a proper file, then it will contain the information about it, and Geopandas will read in that information. And for example, the countries data set that I downloaded from the Natural Earth data has an EPSG number 4326. That's a number you will see quite often because this means that you have data which are in longitude, latitude based on WGS84 reference system. If I look at the districts data set, here you will see it also has an EPSG number. In this case, yeah, another number that denotes, if you would look it up, I can actually do that. So if you have data and you don't know which reference system is it, if it has an EPSG number, you can very easily look it up on epsg.io. And so this is actually one of the EGM zones in which France is located. If you would, oops. Yeah, I don't know exactly what I did. So you have a certain coordinate reference system. Sometimes you want to convert to another system. And for that, Pandas uses the PyProach library that Martin showed under the hood. And there is a method called toCRS that will do this for you. For example, so our countries was in the just latitude and longitude. So if you put it like that.
Excuse me, I don't have a variable countries. I have to load the file, right?
If you run the full notebook, so in the beginning, my examples there it's red. Yeah, sorry. So here you will see this is basically just using your longitude, latitude as x, y. You get some clear distortions of the, in this case, of the Antarctica, the South Pole. I'm just going to remove this for a moment. So, for example, here I convert my longitude latitudes to the Mercator, Web Mercator, I think, or yeah, which has this EPSG number. This will convert, keep the other columns just intact, only convert the coordinates of the all the geometries. And you will see now, if I plot this again, you will see that, for example, the shape of Greenland completely changed. So why is this important in Geopandas that you need to pay attention to the coordinate reference system? Firstly, if you import data sets from different origins, they might have different reference systems. And yeah, if you want to combine them on a single plot, or you want to do some analysis between them, you need to convert them to the same coordinate reference system. Of course, also to make certain plots, you might want to have them in certain system. But an important point is the second one here. So once you start doing like calculations, like you want to know the distance between 2 points or the area, that we already did above. So the calculations for that, which are done under the hood by Shapely, which uses Geos, just assumes that your coordinates are in a plane. So if you use your degrees, latitude, longitude, of course, in reality, it's not on just in a plane. So you will get wrong results. Therefore, if your application cares about correct distances which are in meters and not in degrees, The best thing is always to convert your data to a coordinate reference system which is can be used for your area of interest. For example, for France, there are specific coordinate reference systems which minimize distortions just for France. And then, assuming that that your data are just on a plane is typically, if you are not, is typically fine, unless you really want to know on the centimeter correct distances. But for many applications, then the assumption that Geopandas makes that your coordinates are just XY coordinates in a plane and do calculations based on that. That works typically fine, making sure you choose a good coordinate reference system. So if you know which one to use, in Geopandas is the 2CRS method that you can use for that. What do you need to pass here? You can, which is a bit easier to use, you can pass an EPSG number, but you can also pass the actual description called, for example, I will show it here. Oops. So it's called POI4, has a certain format to describe a reference system like this. And you can also pass that either as a string or as a dict. So such POI4 description can also be used.
Does it have some shortcuts like Mercator or something?
Like
Mercator?
No. So so there are no built-in names or something like that. The only shortcut is the EPSG number for now. There are some other libraries like CartaPy, which has some object-based system with names that you could in principle use and then get from that one the POI4 string. But yeah, in Geopandas itself, the only shortcut is the EPSG number.
But these distortions are only if you go from east to west. If you go from north to south, there's no distortion.
Depending on the coordinate reference system you are using. Indeed, in the one that I showed until now, for north-south, typically no distortion, but for other systems there might be.
Like we have a very long river which goes from east to south, and you have multiple of these ones. You need to use their kind of. If you want to have the long length of the river, then you would need to have multiple conversions. Otherwise, you get.
Yeah, I personally never dealt with data that are too large scale for a single zone, but you can also compute distances. More correctly on the globe. There are some libraries like GeographicLib that correctly calculates between 2 points using a model of the globe, the correct distance. It's just more computationally intensive to do because it's a much more complex calculation instead of just in a 2D Euclidean distance. So if you really need such distance calculations for long distances, like if you want to know the distance between New York and Trento, you either need to choose a very specific coordinate reference system where that is preserved, but that's not that useful. So then there are those libraries available. Here I added a small note on if you want to use Fiona to read in instead of using read file. So basically, but since this is what's happening on the hood, but since Martin already showed that, I will not go in detail here. The main thing I would say that when would you actually want to use this instead of using Geopandas read file function is, for example, if you want to only, you have a big data set and you only want to extract like a small part of it. In this, you can do this by iterating lazily over the file instead of reading the full file in Geopandas and maybe only needing a small part or something. If that is a constraint, that it's a nice use case. But in most cases, I would always try to use Geopandas read file function. yeah, and some other examples, how to construct it manually or from a column with latitude, longitude. I won't go in detail here. So let's continue with the second notebook on spatial relationships. So I'm going for the small examples again. Use the countries, the cities, the rivers. So this morning we saw with Shapely the different possible binary predicates, whether two polygons, whether one polygon is within the other, whether they touch, whether they intersect, whether one is contained in the other. So you have those typical spatial predicates which are all available in Shapely and there's also in Geopandas. Yeah, for the explanation here, I extracted some points and some polygons out of the data sets to have a small example. So I have one polygon, the abstract shape of Belgium. The data set we use here is a very low resolution one, as you can see. Paris, Brussels, and a line between them. And then you can do typical queries like, is Brussels, so this point, is that within this polygon? That should be true. So yes, that is true. On the other hand, so if you inverse it, Belgium contains Brussels. That is also true. But Paris is not located within Belgium. So those typical predicates. Belgium does not contain the full line, but it does intersect. The line intersects with Belgium, for example.
Why do you need the squeeze when you extract the information?
Yeah, so this is a bit a technical thing. So if you look at this, basically, if you do a Boolean operation like this, so based on a certain condition, I want to filter my data frame. The result is always still a data frame. In this case, I know it's actually only a single line. So therefore, and so if I access the geometry column, it's actually a series with one element. And squeeze will always remove dimensions of one. So because I know it's a series of one element, it will give you one element. In this case, for this example, it's a little bit annoying to get out the. One solution would be that you have like the index of your data frame is the name of the country, and then you could simply index it to get out a single element. So, but that's the technical reason for the squeeze. So all those spatial relationships that are available on a single object are also available on the full Geo Data Frame. So before I did Belgium contains Paris, two single objects, just the files. If I do this the full countries data set contains Paris, this will give you a true false for each of the countries. And since this is a Boolean series, we can use it to filter our results. And we can see that indeed Paris is only contained in France. Another example, I took the Amazon River. Yeah, you don't see much about the context, of course. And then I'm interested in all the countries that cross which are crossed by the Amazon River. And in this case, you can see that according to this low resolution data set, it crosses Brazil, Colombia, and Peru. So here you have an overview of all those possible spatial predicates, but the typical ones that are used a lot are like are within and contains, intersects, that are typical ones to use. And there are some links if you want to know the details of exactly what means covers and what means overlaps. There are small differences between them. So let's also do an exercise on those spatial relationships. So we use again our Paris districts and stations dataset. I put here already the imports. So now it's, yeah, you can try to do this exercise. another Geo Data Frame. For example, I could pass the districts. However, this is very often not, it will not give you the result that you want. Because here, in this case, we have a bunch of points, we have a bunch of polygons, and you might assume that it will, for each of the points, calculate the distance to all of the different polygons, which would give you a square distance matrix or something like that, which is not what is happening. It will give you actually some distances and also then some missing values. Why is this? If you do one of those operations or contains within all those Geopandas methods, it will align the both of the objects and just take the distance between the first of stations and the first of districts, the second of stations, the second of districts. So it will do it element-wise and not kind of a cross product of all the combinations. Above we saw some spatial predicates, checking relationship between two objects. You also have some functions that actually create new geometry objects. For example, one of them is the buffer method, which will create a circular area around a certain point or around the line string as well, or polygon. And then we can, for example, calculate the intersection between Belgium and this buffer, which will return you a new geometry. Or we can calculate the union or the difference and things like that. So again, I show it here on the shapely objects, the individual object, but again, this is available as methods on the Geo Data Frame as well. Another useful one is an Airy Union, which will collapse all your geometries of your data frame into a single geometry object. For example, here I filter my countries data set to only the African countries. If I then take the Airy Union of that, that will give me a single shapely object. So you will see that in this case it's a multi-polygon because it consists of multiple polygons, so at least the mainland and Madagascar. I will skip the exercise here because I certainly want to show you still in the last 15 minutes the next notebook, which is on spatial joins. It's a typical operation in spatial analysis. So we have seen in the examples the countries and the cities data sets. But you might want to know, assuming that the information is not included in the data set, you might want to know for each city in which country it is located. A typical point in polygon kind of question. So we will see here how we can do this in Geopandas. So there is also a small section here on how we join data frames in Pandas. Basically, what you need to take away from here is that doing a normal, to call it normal, a normal join, as one like the ones you can do in Pandas, you typically join two data sets based on a column, a certain key. For example, I added here the ISO 3-letter key of the countries. I also added it to the, so this is a cities data set. I also added it to the countries data sets. And since those have a common key column, we can now join those two data frames based on this key column. In that sense, a spatial join is similar. Based on a certain criteria, we will join the information of the two data sets. But in this case, the criteria will not be the equality of a certain key, but will be a spatial relationship. Yeah, this recap I will not, because we go into detail, because we just saw it in the previous notebook. But for example, so for the cities and the countries, so I just extracted here the France geometry. So if you want to know for each city in which country it is located, this is a within operation. So we can check all the cities which are located in France with that method. This gives us a Boolean series. So this says that those cities are located in France. It's not fully correct. Some resolution issues with the data. But OK, according to our data, those cities are located in France. And in principle, we could add here a column France, or we can repeat it for every country. But to automate this, we have the spatial join operation. What do we want to do in a spatial join? We want to transfer information of the one data set to the other based on their spatial relationship. For the cities, we want to add here a name of the country, which is in the country's data frame, based on whether the city is located in one of the countries. How does it look like with Geopandas? It's a function called sJoin. What do you pass to this function? The first one is the data frame to which you want to add information. Our cities, there we want to add a column with the country name. The second argument is the data frame, the Geo Data Frame, that holds this information that you want to add to the first. And then you specify an operation. In this case, which is the spatial relationship, how you want to merge. In this case, the within, because the city should be within the country to join the two rows. And then we can also specify whether we want a left or an inner join. That's a bit more terminology for normal joins as well. Left means that we only keep those rows which are already present in the left data frame, like that. So if we execute this, we call this joint. You will see now that our original cities dataset which had a name and a geometry, we now added information about the country. Maybe, yeah. So you will see, and where multiple cities are located in the same country, it will just repeat this information like those two lines here of the countries datasets. So there is one exercise on a spatial join, but since there is only 10 minutes left, I will go through this in group. So we return back to our districts and stations. And the goal of this exercise is we want to make a visualization, a plot of the different districts, but colored by the number of bike stations that are located in each district. So we can make a density plot of Paris. So we import the different, so the districts and the stations. And the first thing we need to do will be the actual spatial join. We have our stations. That is the data frame for which you want to know for each station in which district is located. So that's the data frame to which you want to add information. That's the first one. Then we specify the districts. And how do you want to join this? It's similar as the previous case. We want to do a point one of the stations within a polygon, so we specify within. If I execute this, you will see now that so those were the original columns of my stations, and now we added here a district name column about the district. So let's call this joint like this. Now we want to know how many stations are there in each district. So how can we do this? Based on this joint data frame. So we have a column with the district name. So we want to count the occurrences of all the districts, of all the different districts. So either you could do this with the value count method, but we can also do this with group by. So I group by the district name, and then I want to know the size of each of those groups using size. I will call this counts like this. If there are any questions during this exercise, please ask. So now we have a series with the number of bike stations for each district. If you want to make a plot of the districts with this information, we want to add this series back to our original district data set. So for that to do this merge, I will convert this count to a data frame, which makes the merge a bit easier to manage. So one way to convert the series into a data frame, if your actual index is useful information, is to reset the index, and then you will get a data frame with two columns, the original index and the values. Like this. Only now I can also specify what I want to be the name of the created column of the original values. For example, the number of bike stations, like this. So now we have our counts for the number of bike stations and the district names, and we can add this information to our original districts. One option is to use the merge operation for this, like this, and I want to do this on the district name column. And so now we did a standard join based on a common column. And you will see now this was our original data set, and we added one column here, the number of bike stations. We'll call these districts 2, like that. I could make a plot now of with the district name, with the number of bike stations. Yeah, so without S again. So like this. But of course, there are some districts with a much bigger area than others. So to make a fair plot, we need to create a new column, or we need to calculate the relative number of bike stations compared to the area. The area we already have seen. We can access this with the area attribute. So the number of bike stations, and we can divide that by the area of each geometry. So since this is a series, this is a series. If I divide two series, it will just do this division element twice. I will, yeah, the absolute values here are now very small because the area is in meters, so you can, of course, do something about that. But I will, for the visualization itself, it's not that important by district, like.
You have a nice for the.
Yeah. Like that. And now we can make the final visualization. I will use here I called it like that. And so now we have, based on our two data sets, calculated with the spatial join the density of bike stations within Paris. And now you clearly see a pattern where you have more bike stations in the city center than more farther away from the center. Are there any questions about this spatial join? That leaves me 2 minutes to say that there is also an overlay operation. What is the basic difference between a spatial join and an overlay is that in overlay you are actually going to combine the geometries of both data frames that you are combining, meaning that you are going to calculate new geometry object by combining those geometries, while in the spatial join you just preserve the geometries of the first data set. For example, in the last example, you have the stations, the points, and you will only add attribute information to them. You don't create new geometries or something like that. While with the overlay, you will create actual new geometries. A very small and a bit like toy example. If here you have Africa, and I created the cities. So there are different cities in Africa. I calculated a buffer of 2 around them. In this case, it's in degrees, so it's a bit difficult to interpret. But then, if you would do an overlay of all the countries of Africa with this cities data set with a difference operation, what does this mean? Is that you would subtract, so remove the area of those buffers in cities from the geometries in Africa, which would give you something like this. So you see that there are now actually holes in our original geometries. So we actually manipulated, did an operation on our geometries. We didn't simply preserve them. So that's the basic difference between a join and overlay in Geopandas terminology. And of course, here you can also do this with a union operation or intersection operation instead of the difference. And let me end with the fact that you can always look at a notebook called More on Visualization, which also shows some other examples to plot, not only with Geopandas, but for example here with GeoPlot, which provides some high-level plotting methods, with CartoPy, which integrates very nicely with different projection systems. Folium is something Martin already explained. And if you want to do some more exercises, there is a case conflict mapping notebook about using a data set about mining sites in Congo, where there, with some analysis based on that. So you can always, do that. It's the same system. Solutions are provided. And if you have any more questions on Geopandas or pandas, I'm here the full conference the next days, so you can always talk to me. Thank you.